All right, everyone, we'll take a look at some related rates problems together here in an attempt to try and better understand this concept, okay? So I've got 4 problems typed out. You should have access to this file if you decided to print it off, or if you're just doing it in your notebooks, that's fine. Okay, but this is like kind of how like related rates problems are going to look. They kind of look like a word problem, and then it's our job to kind of go through the information, determine what the heck are we looking for, what's an equation we're going to use to set up our problem. Then we got to take the derivative. We got to figure out what information we have or need to sub in, and then we can finally solve the problem at hand. So the way I've set this document up is basically, just kind of emphasizing, this process. These are what we're looking for. This is the equation we're going to use. All right, let's take the derivative. What can we sub in? What do we still need to get? Okay, typically this information is not just going to be laid out for you, but this is just to help kind of get you, in the mindset of what you should be thinking about when doing these problems, okay? So let's go through and do some. A circular pool of water is expanding at a rate of 16 pi square inches per second. At what rate is the radius expanding when the radius is 4 inches? So for whatever reason, we have this circular pool of water. It's getting bigger, okay? The rate at which the area is growing is certainly going to be related to the rate at which the radius is getting bigger, all right? And so, let's think about what it is we're dealing with here, okay? So what are we looking for? Well, it asks, at what rate is the radius expanding? We want the rate of change in the radius. The way we would notate then is dr over dt. We want the value of dr dt here. That's what we're going to be looking for. What equation is going to relate our variables? Well, what are we dealing with? Let's see. This right here, the pool of water is expanding at this rate. This is a given rate of change, right? Well, it's the change in what? Notice how it's inches squared per second. When's the only time we square units? If we're talking about area. So we were actually given the rate of change in the area. This is what we would write as dA dt. And like I said in the first video, anything that's given a unit of time like this represents a rate of change, represents a derivative. Okay? So we were given that. Okay, what else were we given? We were told that the radius at some point is going to be 4 inches, okay? So I kind of just jot down, this is what we're looking for, dr dt, and off on the side I kind of make a note, okay, notationally these are the things I'm working with, rate of change of area and the radius. Well, what equation relates our variables? Well, look at the 2 rates of change you're dealing with. You're dealing with the rate of change in area, and you're dealing with the rate of change in the radius. Well, that can simply be put together by using the area of a circle formula. Area equals pi r squared. So the idea is, based on the rates of change you're dealing with, come up with an equation that uses those variables to begin with. Okay, so if I'm dealing with dr, I want an equation that has r in it. If I'm dealing with dA, I want an equation that has a in it. Well, the area formula does that for us, okay? So we realize, all right, we're using area equals pi r squared. Now we can take the derivative of this thing. So on the left, we're just going to have 1 dA over dt. On the right, we're going to have 2 pi r to the first times dr over dt. Okay? And now, what information do we need or have? Well, to solve for dr, we need to know 2 things. We need to know the value of dA dt. We've got that. We need to know the value of r. We've got that. So we don't really need anything. We're good. We know dA dt is 16 pi square inches per second. We know that the value of r will be 4 inches at that moment of time. Notice this is not a rate of change. This is just the value of r at this moment, 4 inches in length. Okay. Only the dA dt, the d whatever dt stuff will come back in terms of rates of change. Okay, but in any event, now we can sub in and we can solve. So dA on the left was 16 pi equals 2 pi, r was 4. I don't make you carry the units in through all the problems. You should give us units in your final answer, but they should be relatively straightforward. If we're solving for a rate of change, it's going to be per the same unit of time as in the problem. We just have to watch the dimensions, whether they're linear, squared, or cubic, Are we talking about length, area, or volume? Okay, but that shouldn't be too big of a deal. So in any event, here we have 16 pi equals 8 pi dr dt. I can go ahead and divide both sides nicely here and get a pretty nice answer. 2 inches per second would be the rate of dr dt here. Okay, it's going to have the same time unit, but I'm not going to square that because we're talking about linear length here. We're not talking about area. If it was, it would be inches squared. If it was volume, I'd be talking about inches cubed. Since it's neither of those things, it's just linear, okay, inches per second. Okay, so again, take a little time to kind of digest that. Make sure you can set up your equation, take the derivative, and then go on and sub in and give me an answer with correct units, okay? Relatively straightforward example here. Let's move into another one. Okay, this one has a bit more reading involved. A 25-foot long ladder is leaning against a wall and sliding toward the floor. If the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? Okay, so there's a lot going on. Just from this information, it can be hard to tell what we're looking for, what equation we will need, and what information we have. When doing related rates problems, it's often going to be helpful to draw a diagram of the situation to help us out. Then it's going to be up to us to label it, notate things, and then be able to figure out what it is we need to figure out, okay? So I'm going to kind of diagram this situation. A 25-foot long ladder leaning against the wall, sliding toward the floor. So here's my wall, here's the floor. We can always assume a right angle with a wall and the floor, okay? And now we have this ladder. Now, in my diagrams, I will sometimes use arrows to indicate direction of motion. So we have this ladder, and let's see, the foot of the ladder, the bottom of the ladder is sliding away from the bottom of the wall. So the bottom of the ladder is sliding this direction. What does that imply about the top of the ladder? If the way I've drawn this, the ladder's sliding out to the right, what's the top of the ladder going to be doing? That's going to be going down, okay? Is the length of the ladder itself going to change as the ladder slides? No. So I'm not going to put an arrow here to indicate that the hypotenuse is getting bigger. It's not. That's always going to be a constant 25 feet. Okay, so I've labeled a 25-foot long ladder leaning against the wall, sliding toward the floor. So I've got the arrow indicating towards the floor. I've got the arrow indicating that it's sliding out from the base. Okay, now the question asks, how fast is the top of the ladder sliding down the wall? So that's this rate. We want the rate of change of this side. When the top of the ladder is 7 feet from the ground. When the top of this ladder is 7 feet above the ground. Okay? So we read through, we've drawn a diagram. It looks like we're dealing with a right triangle, and we are. Okay? Before we can go too much further, we still now need to do some notating. We need to put some letters on the sides of this thing so we have a way of describing and notating the information we're given. You guys can use whatever letters you want, X, Y, and Z. I'm going to use A, B, and C here. I'm going to use A for the base of the triangle, B for the height of the triangle, and C for the hypotenuse. That's what I'm going to use. Now, in terms of notating, what is 25 feet here? Well, that is just the value of C. So here's what we know. We know C is going to be 25 feet. The foot of the ladder is sliding away from the bottom of the wall at a rate of 15 feet per second. That's per unit of time. That's a rate of change. It's the rate of change of the bottom side of the triangle. That's the value of dA dt here. So we know that. How fast is the top of the ladder sliding down the wall? We want the rate of change of side B. That's what we're solving for. We want dB over dt. That's the value we're going for. When the top of the ladder is 7 feet from the ground, well, what did I label this side of the triangle? Side B. So B itself is going to be 7 feet. Okay. And I think that's about as much as we're going to get at this point, okay? So look, this is a lot of information. Part A, what are we looking for? Well, we already realized we're looking for the value of dB over dt, the rate of change of this side, the rate at which the top of the ladder is sliding down. So dB over dt. What equation relates our variables? Well, what's going to relate A, B, and C here? Pythagorean theorem. Okay, now we take the derivative always with respect to time. So this is going to be 2a to the first dA over dt plus derivative of b squared, 2b dB over dt, and finally 2c dC over dt. And while it's not necessary, I will go ahead and divide both sides by 2 just to simplify this up a little bit, okay? All right, now let's think about what we have and what we need. Ultimately, we want to solve for dB dt. That's what we're solving for. So we're going to have to know a whole bunch of things. We got to know the value of a to sub in. We actually don't know that yet. So we're going to need to pick up the value of a. That wasn't given. We need the value of dA dt. We have that, okay? We're going to need the value of b. We have that. We're going to need the value of c. We have that. And then we're also going to need the value of dC dt, okay? So we need a and we need dC over dt. Those are two things we need to figure out before we can actually go on to solve for the rate of change of side B. Okay, so let's start with A. That shouldn't be too bad here. We know that at this particular moment, one leg is 7 and the hypotenuse is 25. So what can I actually do to solve for A? Well, I can use Pythagorean's theorem using those two values. When B is 7 and the hypotenuse is 25, what is that going to make side A? Let's see. So a squared is going to be 576, and if you take the square root of that, it is a perfect square. We end up with 24, okay? So we were able to come up with the value of A. We got that. And now we need the value of dC dt, which represents the rate of change of side C. We actually know this value without maybe even realizing we know it. What did we say earlier? Why did we not put arrows on this? Because the length of the hypotenuse itself is not changing. As the ladder slides towards the ground, its length itself is not changing. If something is not changing in length, it is constant. So what do you suppose that makes dC over dt? If side C is a constant, then its rate of change is 0. Okay, since C is a constant, dC dt will equal 0 here. So we have now everything we need. Let's go ahead and solve. So again, just the general equation looks like this at this point. And I'm going to sub in. So A was 24, dA dt was 15, B is 7, dB dt is what we're solving for. C is 25, but doesn't much matter because the rate of its change was 0. So we get 360 plus 7 dB over dt equals 0. So 7 dB dt is negative 360. So dB dt is negative 360 sevenths. And then again, the length units here are are feet per second. All right. And again, you can use a calculator for this stuff. It's fine. Just round according to what WebAssign says, okay, or what the instructions are for any given problem. I just did this one exact value. Now, what do you notice about our rate of change? Hopefully you notice that it came back negative, and that should make sense. Why did the rate of change of side B come back negative, do you suppose? It's not so much because the side is going down. It's more because of what's happening to this length. Does that side increase or decrease as the ladder comes down? It's actually decreasing in length. And this is going to be something we talk about in later lessons, how we can tell when functions are increasing and decreasing. But you probably remember a little bit of that from pre-calc, right? If a derivative is negative, the thing it came from, the function it came from, is decreasing. So that's why dA is positive. The length of side A is getting longer as the bottom of the ladder shoots out. Rate of change of B is negative because the length of side B is getting shorter as the ladder drops down. Okay, so positive and negative rates of change do have physical context, they do have meaning, but we'll worry more about that a little bit later in the course. Again, for now, can we set up these equations? Can we notate? Can we drop in the values and solve for what we're looking for? Okay, that's what it's about right now. Okay, next up, a spherical balloon is expanding at a rate of 60 pi cubic inches per second. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? Recall the equations for volume and surface area of a sphere. Volume 4/3 pi r cubed, and the surface area formula of a sphere is area equals 4 pi r squared. Okay. So again, as we go through, it's like, I kind of am in the habit of kind of notating this stuff when I see it. I see a rate of change per unit of time. I notice that it's cubic units. When do we cube units? When we're talking about volume. This must be the rate of change in volume that they're giving us. So we can notate that. How fast is the surface area expanding? What are we looking for? We're looking for the rate of change in the surface area then. We want dA over dt. Okay, what equation will relate our variables, okay? Well, what's the other variable we're dealing with? The radius is going to be 4, so we know that we're dealing with that. So if you think about it, look, we're dealing with the radius, we're dealing with the rate of change of area, and we're also dealing with the rate of change in volume, okay? If you notice between these two formulas, there's one that relates volume in R, and there's one that relates area in R, okay? But there's not one that's relating V and A, okay? So we're not going to try to find one equation that relates the two. This is going to kind of be like a 2-for-1 related rates problem. Use a little common sense. If we're looking for the rate of change of area, will it make more sense to take the derivative of the volume formula, or will it make more sense to take the derivative of the area formula if dA dt is what we're after? Well, we're going to use this formula because we want dA dt. There's no a here. This doesn't help us right now, okay? So let's take the derivative of the area formula. Excuse me, I just did there. So we're going to use area equals 4 pi r squared. Taking the derivative, we're going to get 1 dA over dt on the left. Over here, we're going to get 8 pi r to the first times dr dt on the right, okay? Now, again, we're solving for this. What do we need to know? We need to know the value of r. We know that. We got that up at the beginning. R is 4. But we also need the value of dr dt. That was not given anywhere. And so this is why I think I consider it like a 2-for-1 related rates problem. Before we can solve for the rate of change of area, we have to come up with the rate of change of r. Well, the only other information we haven't yet dealt with was that bit about the rate of change in volume. So maybe there's going to be a relationship between dV and dr that we can use to our advantage here, okay? So on the side, I'm now going to look at the volume formula. And now I'll take the derivative to get dV over dt into play. Okay, so if we take the derivative of v, we get 1 dV dt. On the right, we bring down the 3, they cancel. We're left with 4 pi r squared times dr dt. And sure enough, here's an equation that relates dV and dr. We actually know that dV was 60 pi, and we know that r is 4. And sure enough, we can now use this to solve for dr. Once we have that, we can go back, sub it in, and solve for dA. Okay, so here we're going to get 60 pi. Let's see, that's 16 times 4 is 64 pi. And so I'm going to divide by 64 pi on both sides. And dr dt is 60 over 64, or 15/16 for short. Units would just be inches per second for the rate of change in the radius. Now that we know that, we can come back to this and we can go ahead and solve. So again, dA dt, 8 pi r is 4, and dr dt is 15 over 16 inches per second. And let's see, if we clean this up a little bit, that's going to be 32. 32 over 16 is 2, times 15 is 30, pi, and because it's area, it would be inches squared per second. And there you have it. Okay, so again, take your time, watch it once or twice if you need to, but basically we had to use some given information in one form of related rates problem to solve for DR, then we can come back and solve for what we're actually after. Pretty common type of problem here, okay? And then the last one for this lesson, an underground conical tank standing on its vertex, think ice cream cone, is being filled with water at a rate of 18 pi cubic feet per second. If the tank has a height of 30 feet and a radius of 15 feet, how fast is the water level rising when the water in the tank is 12 feet deep? Recall the equation for volume of a cone is volume is 1/3 pi r squared h. In terms of our diagram, we have a conical tank underground here, standing on its vertex. That's the tip. Okay, so here's the tank. Okay, it's being filled with water. So here's a water level I'll draw. And which way is the water level going? Well, the water level will be rising. It's going up. The tank has a height of 30 feet. And it has a radius of 15 feet. How fast is the water level rising when the water is 12 feet deep? So the depth of the water is 12 feet. Okay? See you next time. So let's go ahead and see what we can do here. We still don't have any letters. Well, we do. We have an R for the radius of the tank, but I'm going to put an R here in blue representing the radius of the water, and I'm going to put an H here in blue representing the height of the water. And that's important because it says how fast is the water level rising when the water level is 12 feet deep. So we know that the value of H itself is going to be 12 feet. And we want the rate of change of H, the rate at which that water level is rising. dH over dt is what we're looking for here. Okay. And let's see, what equation relates our variables? Well, we really only have one equation to use here. We have this volume of the cone formula. So volume equals 1/3 pi r squared h. Okay, oh, and what's one thing I forgot to notate? Jeepers, that's important. That 18 pi cubic feet per second. Well, it's per unit of time, so it's a rate of change. What is it the rate of change in? Well, it's cubic feet, so it's the rate of change in volume. Okay, so that is being given to us here. Okay, and so here we have something that can relate V with H. Now notice we also have this R piece here. So when we go to take the derivative, what are we going to have to use? Product rule. Okay, so dV over dt equals, the derivative of the first piece is going to be 2/3 pi r to the first times dr dt. There's the derivative of the first part times the h, the second part. Plus, I'm going to keep the first part of this and multiply by the derivative of the second part. That would just be dH dt here. Okay? And now, again, a little more involved. We have the product rule to get through, but shouldn't be too bad. And now, let's see. We ultimately want to solve for dH dt. So here it is. So what do we need to know? We need to know the value of dV dt. We got that. That we got. We need the value of R. This we don't actually know. This, remember, represents the radius and height of the water in the tank. So we need the value of the radius of the water in the tank, not this 15. That's not what we're interested in, okay? We need the height of the water. We got that. That was 12. We also need dr dt. That we don't have anywhere. The rate of change of the radius of the water in the tank, okay? And so, there's a lot we need to do here. Okay, so ultimately we're looking for dH dt. We know what dV is, we know what H is, but we still need R, and we still need dr over dt. Okay, so we have to go about figuring out what those things are. Hi everybody, I'm just doing a lesson. You guys should just check Google Classroom. All right, and so this cone problem, there's a reason why I saved it for last, because it's the toughest of the derivatives, but it also requires us to understand something about cones. Every cone is different. But in every cone is different, but within every cone there exists a relationship between its radius and its height. So in this cone, what do we notice? Well, the height of the cone is 30, the radius of the cone is 15. So what is the height compared to the radius? It looks like the height is exactly twice the radius in this particular cone. Okay? And that's going to be proportional to the radius and height of the water. I mean, what we have here, if you remember anything from geometry, is we have similar right triangles, and similar right triangles are proportional. Okay? Just one of the layers of calculus that makes the course tough is remembering some of these old prerequisite skills, okay? But in this sense, in this particular cone, the height is twice the radius. Now, if you think about it, we actually want to know what r is, so I could divide both sides by 2 and get that the radius is half the height. So coming back up here, you know, if we know the height was 12, what's the radius going to be if it's half that? Well, it's going to be 6. All right, so we now know the radius is 6. So we can sub 6 in for our r's. And the last thing we need to know is the value of dr dt. Well, guess what? We can, again, use this to get it. I can say, look, the derivative of the left side is 1 dr dt. The derivative of the right side is 1/2 dh dt. And so while I don't know exactly the rate of change of the radius, I do know that it will be equal to 1/2 the rate of change of the height. And since dh dt is what we're solving for, I can actually sub that in here. All right. So let me kind of bring this down. All right. We've got dv dt equals 2/3 pi. R was 6. Dr dt is going to get replaced with 1/2 dh dt. And h was 12. So there's that part of it. Plus 1/3 pi. Make a little more room here. R is 6 squared, and then times dh dt. Okay, so I'm just subbing into that big long equation up there. And what am I missing? The value of dv dt, which was 18 pi. Okay, so let's see. I'm going to clean this up a little bit here. Let's see. 2 times 3 is 6 in the denominator. Those will cancel. Here we get 24 pi dh dt. This is 36, 1/3 of which is 12 pi dh dt. And again, go at your own pace here with the algebra. I can combine these like terms. 24 pi of these plus another 12 pi of them gives me 36 pi dh dt's. And now I can solve for dh by dividing by 36 pi. And this comes out pretty nice. We get exactly 18/36, or 1/2. Let me double check these units here. We're dealing with feet per second for the linear units. All right, and that's the rate of change in the height here. 1/2 foot per second would be the rate of change in the height. Okay, cone problem's a little bit more difficult. It was a tougher derivative, having to use the product rule. We had to really focus on the relationship between h and r. We had to find out what r was. We had to figure out what dr dt was. There's actually a slightly easier way, which I'll now show you, okay? Basically, you know, here's our formula. Volume equals 1/3 pi r squared h. Now, we had info about dv dt, and we wanted dh dt. We were not given anything about r, we didn't know anything about dr dt, and we honestly don't care too much about it. So we can actually make this long problem into a much shorter one if we investigate the relationship between the radius and the height at the onset. It's still going to be the case that the radius is half the height. I'm actually going to sub that in for r now. So watch what happens when I replace r in the initial volume formula. Because in this particular cone now, I know that the radius is half the height, but now I have a volume formula just in terms of h. Okay, no more r. I'm going to clean it up a little bit here. I got to square the 1/2 h. That'll be 1 over 4 h squared. And now I'll clean this up. This is going to give me a 1/12 pi h cubed. Look at our volume formula now just in terms of h. There's no product. There's no product rule. There's no mention of r anywhere. Now when I take the derivative of both sides, I'm going to get 3/12 pi h squared times dh dt. Again, we know that dv was 18 pi, and we know that h was 12, and we didn't have to worry about r at all, okay? And let's see how this works out. Well, 12 squared is 144, divided by 4 is 36. And look at that, we end up exactly in the same spot we ended up with up here with a heck of a lot less effort. Same end result. Okay, so again, you know, the relationship with cone problems between R and H is crucial. I recommend trying to see it up front, subbing it into V, and then making life a little bit easier on yourselves. In the next lesson, we'll focus a little more on rates of change of angles with trig functions, okay? As always, reach out with any questions. Take care.